So I'm guessing you want to go a bit deeper than the basic, huh? Like beyond those simple diagrams.
Yeah, definitely.
We're looking at those regions around an atom's nucleus where electrons are most likely to be found, right?
Absolutely. And you know what's really interesting? Those simple shapes we learn about, the SPG and F orbitals, they're just the tip of the iceberg.
Oh, yeah, for sure.
They dictate pretty much everything about how elements behave, how they bond, how they form molecules, the properties of materials, even the colors we see.
Okay, but before we go too far, let's make sure we're all on the same page. We know orbitals, those are spherical. p-orbitals, those are the dumbbell-shaped ones. And then D and F get even more complex.
Yeah,
But the important thing is that each of those shapes, they represent different energy levels within an atom. Right.
exactly. And as we go to higher energy levels, the number of each type of orbital, that also increases.
Okay.
So like at the first energy level, you've only got one orbital. But then at the second level,
Yeah.
you get one s-orbital, but then three p-orbitals.
Oh, I see. So it's kind of like adding more rooms to a house as you build more floors.
Perfect analogy. And just like you wouldn't just throw furniture into any random room, electrons fill those orbitals in a specific order. It's not random chaos.
Right. They follow the off-ball principle.
Yes,
Always trying to find that lowest energy state, right? Kind of like finding the comfiest spot on the couch.
exactly.
But I do remember from chemistry class there were some other rules too, right? Like Hund's rule and the Pauli exclusion principle. What do those do in all of this?
Oh, those are crucial. Those are key to understanding how those electrons actually behave within those orbitals.
Okay.
So Hund's rule, that one tells us that electrons, they actually prefer to occupy different orbitals with the same energy before they start doubling up in the same one.
Right.
It's like if you've got multiple comfy chairs, you'd rather have your own space before having to share one, right?
Makes sense. So maximizing personal space even at the atomic level.
Exactly. And then we have the Pauli exclusion principle. And this one says no two electrons in an atom can have the exact same set of four quantum numbers.
Ah, quantum numbers. That's right. It's like each electron's address telling us where it lives within the atom.
It's like an ID card. Yeah,
Right.
absolutely. So you've got the principal quantum number, m, that tells you the main energy level.
Okay.
Then you've got the angular momentum quantum number, L, that one gives you the shape of the orbital.
Okay.
Then you've got the magnetic quantum number, M, specifies the orientation of that orbital in space. And finally, the spin quantum number, Ms, that indicates the electron's spin.
Wow. So each electron really does have a unique address then. But, even though we visualize these orbitals as these smooth shapes, we're really talking about probabilities, aren't we? It's not like we can actually pinpoint exactly where an electron is.
That's where quantum mechanics gets really interesting. It's not about precise locations. It's all about probabilities. And the shapes of these orbitals are actually derived from solving the Schrödinger equation.
The Schrödinger equation, right.
It's a mathematical equation that describes the wave-like behavior of electrons.
Okay, I think I'm going to have to trust you on the math for this one, but can you give me like a non-mathematical explanation, the big picture? What does solving that equation actually tell us about those weird orbital shapes?
Basically, it tells us the regions where it's highly probable to find an electron. So it's not like it's definitely here, but it's like it's probably somewhere around here.
Uh-huh, okay.
And these regions, these areas of high probability, that's what gives rise to the shapes we associate with the sp, d, and f orbitals.
So those shapes aren't just like, randomly drawn. They emerge from the actual mathematical description of how electrons behave in atoms.
Exactly. And what's even more fascinating is that the angular momentum of an electron, so that L number we talked about, that has a direct influence on how complex those shapes are.
Now, that is something I've always wondered about. Why does angular momentum seem to, dictate whether an orbital is a simple sphere or something far more intricate?
Think of angular momentum as a measure of an electron's orbital motion around the nucleus.
Okay.
The higher the angular momentum, the more complex that electron's motion is going to be. And that complexity, it's reflected in the shape of the orbital.
So an s-orbital with L is 0, that means the electron's motion is pretty straightforward.
Yes, zero angular momentum, very symmetrical motion around the nucleus. And that results in that nice, simple spherical shape. But then as we go up to like LES1 for p-orbitals, the electron's motion gets more complex, and that leads to those two lobes, those dumbbell shapes. And with d and f orbitals, it just keeps getting more and more complex.
Which makes sense because their shapes are just wild. But, okay, if there's this pattern of increasing complexity with higher angular momentum, why stop at f-orbitals? Why not g-orbitals or h-orbitals? Could there be even weirder shapes that we just haven't discovered yet?
Oh, theoretically. Totally possible.
Really?
The math doesn't Doesn't say those can't exist, but here's where things get really interesting.
Oh, okay. Is there like a practical limit? Like maybe those hypothetical orbitals are just too bizarre to actually exist in the real world?
It's not about being bizarre, it's about energy. Those theoretical orbitals, they would require extremely high energy levels, way beyond what we normally see in stable atoms.
Ah, okay. So even though the math might allow for infinite possibilities, the laws of physics, and the stability of atoms, those kind of put a limit on what can actually exist.
Right, those SPD and F orbitals, those are kind of the sweet spot for creating stable atoms and molecules.
Right.
And that's more than enough complexity to lead to the incredible diversity of the universe as we know it.
That's a perfect segue to what I wanted to ask next. We've been talking about these orbitals in isolation, but how do they actually interact with each other? Like, how do they come together to form the molecules and materials that make up, well, everything around us?
That's where we get into chemical bonding. And it's all about those valence electrons, the ones in the outermost orbitals, trying to find a more stable configuration.
So are we saying these orbitals, these electron clouds, they actually reach out and connect with each other?
In a way, yes.
Wow.
And there are different ways they can do that, which leads to the different types of chemical bonds. And each of those bond types has its own unique properties.
This is where it gets really exciting. We're going from like the theoretical world of orbitals to the actual stuff we can see and touch.
Absolutely. And understanding those bonds is key to unlocking the secrets of, well, everything, from why water is a liquid to how metals conduct electricity.
Okay, now I'm really hooked. Let's unpack these different types of bonding and see where it takes us.
Let's do it.
Okay, so we've got those atomic orbitals figured out, electron clouds, specific shapes, energies, all that.
Yeah.
But now I'm really curious about how they actually interact. Like, how do they create those molecules and materials?
That's where chemical bonding comes in. It's like, think of it this way. Atoms are most stable when their outermost energy level is totally full of electrons.
Okay.
So to get to that stability, they're going to share or transfer electrons with other atoms. That's the heart of chemical bonding.
So it's kind of like a game of musical chairs, but for atoms. Everyone's trying to find a seat, a complete set of electrons.
Perfect analogy. And depending on how they get that full outer shell, we get different types of bonds. The main two are ionic and covalent.
Right, those ring a bell. But can you remind me, how are those different, like at the orbital level?
Sure. In ionic bonding, one atom basically donates an electron to another atom. This creates ions, one's positively charged, the other's negatively charged, and they attract each other just like magnets.
Oh, okay.
Classic example, table salt sodium chloride.
Right, right.
Sodium, it loses an electron to become positive, while chlorine gains that electron to become negative.
So it's like a clean breakup. One atom gives up the electron completely, the other one takes it.
Exactly. And those opposite charges, those ions, they're held together by strong electrostatic forces. And that's why you get things like salt, which has a really high melting point.
Makes sense.
Now, covalent bonding, that's a bit different. Here, the atoms are sharing electrons. They don't completely transfer them.
Okay.
It's more like a partnership. Both atoms contribute to this shared pool of electrons.
So instead of hogging the electrons, they're playing nice.
Exactly. And this sharing happens within overlapping orbitals.
Okay.
Each atom throws in one electrons to form a shared pair, and that helps them both fill their outer energy levels.
I see. I see. So like with water, each hydrogen atom is sharing its electron with the oxygen.
Exactly, creating that nice stable water molecule with strong covalent bonds.
Okay, so the difference is ionic bonding is that complete transfer of electrons, you get charged ions. Covalent bonding is more about sharing those electron pairs within those overlapping orbitals.
You got it. But it doesn't end there. Even within covalent bonds, the sharing isn't always equal. Sometimes one atom's going to have a stronger pull on those shared electrons.
Oh, interesting. So like a tug of war, but one atom's a bit stronger.
Exactly. And that unequal sharing creates a partial charge separation within the molecule. The atom that's pulling harder on those electrons, it becomes slightly negative.
Okay.
The other atom becomes slightly positive.
So it's not a full-blown ionic situation with distinct ions, but there's still that charge imbalance within the molecule.
Right. And this is what we call polarity. And it has huge implications for how molecules interact with each other.
Okay.
Like, think about water again.
Yeah.
The oxygen atom pulls stronger on those shared electrons, right? So the oxygen end of the water molecule, that becomes slightly negative. The hydrogen ends slightly positive.
And that's why water is such a good salt.
You got it.
Because those slightly charged ends can attract other charged particles.
Exactly. It can dissolve a wide range of substances. It's essential for life as we know it.
Wow, that's incredible. Okay, so we've got ionic bonds, covalent bonds, even polar covalent bonds, all coming from how those atomic orbitals interact. And each of these bond types, they lead to different properties in the molecules and materials they form, right?
Absolutely. The type of bonding, the shape of those orbitals, how they overlap, all that contributes to a substance's unique characteristics. That's why salt is brittle, diamond is hard, and plastic is flexible.
It's amazing. So these electron clouds, these orbitals, they ultimately determine whether something is solid, liquid, gas, whether it's strong or weak, conductive, or insulating.
It all boils down to those electron interactions and how those orbitals, those electron clouds, interact with each other. But there's another type of bonding we haven't touched on yet, metallic bonding.
Oh, right, we mentioned it briefly earlier. Is this where those delocalized electrons come in?
You got it.
Okay.
In metallic bonding, those valence electrons aren't stuck to individual atoms. They're free to move throughout the entire material. It's like a sea of electrons.
So they're not confined to those specific orbitals. They're roaming free within the metal.
Exactly. And that's what gives metals their unique properties. The electrical conductivity, their malleability, that shiny luster.
Oh, wow. So those free-flowing electrons, they're why we can bend metal, why it conducts electricity so well, and why it's got that characteristic shine.
Exactly. It's the perfect example of how that electron behavior at the atomic level translates to those big, noticeable properties we see every day. But there's another connection between orbitals and our world that's really fascinating. Color.
Ooh, color. I wouldn't have thought about that, actually. How does the arrangement of electrons affect the colors we see?
So when light interacts with matter, electrons can absorb energy from specific wavelengths of light, and then they jump up to higher energy levels.
Okay.
And the wavelengths that get absorbed, those correspond to specific energy differences between those orbitals.
So it's like those electrons are picky eaters when it comes to light. They'll only absorb certain colors.
That's a great way to put it. And the colors that aren't absorbed, those are the ones we see. They're reflected back or they pass through the material.
Ah, okay. So the arrangement of electrons in those orbitals is what determines which wavelengths of light get absorbed and therefore what colors we actually see.
Exactly. And this applies to everything, like the vibrant colors of a flower, the deep blue of the ocean, even the colors we see in stars.
Hold on, stars. We're talking about the colors of stars now. How do orbitals factor into something that vast and distant?
Okay, so the light that stars emit, that's produced by nuclear fusion in their core.
Right.
But the specific colors, or what we call spectral lines that we observe, those are influenced by the composition of the star's atmosphere.
So the light from the star's core is passing through its outer layers.
Right.
And those layers, they're made up of atoms with their specific electron configurations.
Exactly. As that light passes through, those atoms are going to absorb specific wavelengths based on the arrangement of their electrons. And by analyzing these absorption patterns, astronomers can figure out what the star is actually made of.
Oh, wow. So it's like taking a fingerprint of a star, revealing its ingredients based on how its atoms are interacting with light.
Precisely. And it all goes back to those tiny atomic orbitals and how they dictate those energy levels of electrons.
It's just wild to think that something as, I don't know, abstract as the shape and arrangement of electron clouds can actually have such huge effects on literally everything around us. But okay, I have a question. If the rules of chemical bonding are so well defined, is there any room for randomness, like spontaneity in how molecules actually form?
That's a great question. The fundamental principles, they're clear, yeah?
Right.
But the sheer number of atoms and molecules involved, plus all the environmental factors, that leads to incredible complexity.
So while the individual interactions are predictable, the bigger picture can get pretty unpredictable.
Exactly, like protein folding. The sequence of amino acids and those bonding rules, those determine how they interact.
Yeah.
But that final 3D structure, super complex, influenced by tons of factors.
So it's like, we've got the rules of the game, but the actual game itself can play out in so many different ways.
That's a fantastic way to put it. And that's what makes chemistry so cool. It's this interplay of deterministic rules and this emergent complexity that leads to all the diversity and all those amazing properties of the world around us.
We've covered so much, from orbital shapes to how they determine bonding, material properties, even color and the composition of stars. It's really starting to click how these abstract concepts have such real-world consequences. But I'm curious, how did scientists even figure out those orbital shapes in the first place? Like, you can't just look at them under a microscope.
That's a great point. It's a real detective story, a story of scientific discovery.
Right.
And it took centuries, really. It wasn't just one moment. It was lots of observations, experiments, and refining those models over and over again.
So it was a team effort, scientists building on each other's work, slowly getting a clearer picture.
Absolutely. The earliest models of the atom, things like the plum pudding model, they were based on limited data. They couldn't explain everything scientists were seeing. But then came those groundbreaking experiments like Rutherford's gold foil experiment.
Oh, yeah.
That one revealed that the atom had this tiny, dense nucleus.
That must have been a big surprise.
It was huge. And it led to Bohr's model, with electrons orbiting the nucleus in those specific energy levels. But even that model had limitations. It wasn't until quantum mechanics and the Schrödinger equation came along that we got to the modern idea of atomic orbitals as probability distributions.
Ah, okay. So those weird complex shapes, they're not just random doodles. They're mathematical representations of the most likely spots for an electron based on this wave-like behavior from quantum mechanics.
Exactly. It's a good reminder that science is a journey, and what we know about the universe is always changing. What we understand about orbitals today is built on the work of so many scientists who came before us.
That's a good perspective to keep in mind, for sure. It's not about memorizing facts. It's about understanding that process of discovery, how our knowledge evolves over time.
Exactly. And who knows what we'll discover next? What new insights about atomic orbitals are waiting for us as we explore the quantum world?
Okay, this has been an amazing journey. We started with these seemingly simple orbital shapes and ended up talking about their impact on, well, everything, from colors to the fate of stars.
It really shows the power of scientific inquiry. Those tiny building blocks of the universe, they hold so many secrets.
All right, to our listener, thanks for joining us on this deep dive into atomic orbitals. We hope you've enjoyed it. Keep those brains buzzing and those questions coming. There's always more to explore in the world of chemistry and beyond. Welcome back to our deep dive. We're exploring the world of atomic orbitals, and we've come a long way from those basic shapes to how they affect bonding, properties of materials, even colors.
Yeah, now we're going to zoom out even further. We're going to look at how these tiny electron clouds can actually impact the entire universe, the cosmos.
Okay, hold on. So we know the arrangement of electrons in orbitals affects things like, strength, flexibility, color, but how does that translate to something as big as the universe?
Well, let's think about the life cycle of stars.
Okay.
Stars, they're born from these massive clouds of gas and dust. And it's gravity, the attraction between all those particles, that starts the whole process of star formation.
Right, right. So we're talking about huge clouds of what, mostly hydrogen and helium.
Exactly. And inside these clouds, the atoms are constantly bumping into each other.
Yeah.
And those collisions, they can actually excite the electrons up to higher energy levels.
And then when those excited electrons fall back down to their ground state, they release energy, right, in the form of light?
Exactly. And the specific colors of light, or wavelengths, that are emitted, those depend on the energy differences between those orbitals.
Okay.
So the composition of the cloud, like what types of atoms are in there, that's going to influence the colors of light we see during those early stages of star formation.
So even before a star actually ignites, before it starts doing nuclear fusion, those orbitals are already playing a role in the light that we might observe.
That's right. And once a star does ignite, once nuclear fusion starts,
Yeah.
those orbitals are critical for understanding how energy is actually produced in the core of the star.
So, okay, let's talk about nuclear fusion. We know it involves fusing those hydrogen nuclei to form helium,
Yeah.
releases tons of energy, but where do orbitals fit into all of this?
Well, for fusion to even happen, those atomic nuclei, they have to overcome their repulsion. They're both positively charged. They're going to get close enough for the strong nuclear force to take over.
Yeah, right, right.
And the way the electrons are arranged in those orbitals, that affects how easily those nuclei can get close to each other.
So those electron clouds around the nuclei, they can actually either help or hinder the whole fusion process.
Exactly. And this has huge implications for, what types of stars form, how long they live, all that.
Wow, that's fascinating. It's like these tiny electron clouds are influencing the fate of stars over billions of years.
And it goes even further. It affects things like supernova, the death of stars.
Oh, wow. Okay, now we're talking about some of the most powerful events in the universe. So how do orbitals play a role in these explosions?
When a really massive star runs out of fuel, it collapses under its own gravity. And this collapse can trigger this runaway fusion reaction. That's what leads to a supernova.
And during these explosions, that's where those heavier elements, those elements heavier than iron, they're created and scattered throughout space, right?
Exactly. And to form those heavier elements, you need to create new orbitals as you add more protons and neutrons to those atomic nuclei.
So those extreme conditions in a supernova, those are like pushing the limits of what's possible in terms of electron configurations and orbital arrangements.
Exactly. And those brand new elements, they've got their own unique orbital structures, and then those become the building blocks for the next generation of stars and planets.
Wow, so it's mind-blowing. These electron clouds, they're shaping matter here on Earth, but they're also influencing the evolution of stars and the creation of elements throughout the entire universe.
It shows how everything is connected, right? From the smallest atoms to the biggest stars, it's all linked.
This has been an incredible deep dive. We started with those seemingly simple orbital shapes, and we've explored their impact on, well, everything, from colors to stars.
It's really amazing what we can learn by exploring these fundamental building blocks of the universe.
So to our listener, we hope you enjoyed this deep dive into atomic orbitals. It's a vast and fascinating world, and there's always more to discover out there. So keep exploring, keep those brains buzzing, and keep those questions coming.